This begins EE 544 on Thursday, February 27, 2014.
Good afternoon, everybody. Welcome to E544. One final reminder. No, not final reminder. I will remind you again next Tuesday and Thursday. The midterm is Friday, March 7. You have the choice between 4 to 6 or 6 to 8 p.m. By the way, you don't need to tell me which one you are. You just come. But always keep in mind that if you are in the 4 to 6, you cannot leave the room early. Which means that if you finish the exam in 1 hour, you cannot leave. You have to stay until the exam is over. Clear? Keep that in mind. You will not be able to finish the exam in 1 hour. So this is irrelevant. But the important thing is the new room. We are not going to be in this room. It will be in the Salvatore 101. Salvatore 101 is in the computer science building. The first room in that building is the Salvatore 101. You won't miss it. I mean, it's there. Clear? Okay. And I will be posting tonight or tomorrow morning some problems for you to practice. And I will also post the solutions to homework number. Did I post the solutions or not yet? Okay, I'll post solutions to homework number 2. Clear? Can you remind me, please? Okay, good. This is all you are doing it with no, I mean, you know, it's just a title that you are, let's say, you are the president of the class. No extra credit. Okay, good. Now, let's continue our discussion from last time. We started talking about impedance matching, impedance transformation and matching. And again, as I told you, this is what RF is all about. And this is how they describe. RF is all about matching. RF is all about matching. Okay, we saw the reasons for matching is to provide for maximum power transfer, to provide for what? To provide for low noise figures, to provide for maximum efficiency of the use, to provide for minimum reflections. I will show you the reflections in just a second when we talk about the transmission line. We went through the derivations of the impedance matching, and we ended up with a result. Very interesting result is that for us to have a power matching, maximum power transfer, the load resistance or the load impedance needs to be what? Needs to be the complex conjugate of the source impedance. If the load and the source happens to be what? Happens to be real, then they are going to be what? They are going to be equal. Otherwise, it will be what? The complex conjugate of each other. And for this case, we found that the power is equal to what? Vs square over what? 8RS. This is the maximum power transfer. Maximum power that can you deliver to the load from a given source. Clear? Okay. We went through the transformation techniques. The first one, of course, is a transformer. Now, we call it an ideal transformer. In what sense? In the sense that the input power is the same as what? As the output power. Now, we saw that the relationship, if this is 1 to n, by the way, in the exam, if there's a problem with this, be careful and look at this carefully, whether it's n to 1 or 1 to n. So, I mean, don't rush right away, use the equations. Be careful about that. In this case, it's 1 to n, which means what? It means V2 is equal to NV1, and I2 will be the other way around, 1 over n, I1. And we did all of this analysis there. We ended up with a result that what? That the input impedance, for example, is the N, and the load impedance, the 2, is related by what? Or are they related to what? By square of the what? Of the number of what? Number of turns. Clear? Number of turns. We went and then studied what? We studied the LC networks and LC type networks as what? as impedance transformers, and we said that this is what, ideally, this is the most suitable type because it does not introduce any losses. So you can put the impedance matching network into the whole thing without introducing any additional losses. But this is, again, easier said than done. In reality, whenever you put a matching network into a circuit, remember the matching network is this. This is the load, and this is the what? The matching network. And this is the what? This is the source. Or whatever, G, our generator or our source. I don't know what did we designate it last time. Okay, this is RL, for example. This one will introduce what? Will introduce a loss that we refer to it as what? Insertion loss. Insertion loss. When you see the word insertion loss, when you put a filter, for example, a filter, which is a passive device, it will introduce what? Some losses that you need to take into account when you do their budget. Okay, now, the L match, the LC match, again, as I told you, it is used for what? Matching for narrowband networks, narrowband systems, not networks, sorry, narrowband systems. And the reason for that is that because the matching is actually done in what? In just a single frequency, which is what? Which is omega naught. You are hoping that the bandwidth is narrow enough that the frequencies around, clustered around the center frequency, the matching is what? Is still good enough. Clear? Oh, now we said that we do have an L shape. Always remember, when the L, this is, in other words, it's pointing, this L is pointing toward here. Yes? This, whenever it's pointing toward here, this resistance is what? Higher than this resistance, which means what? You are transforming what? High to what? Low. Let me show you one. We'll get to it in a minute. Just to make sure that here, for example, this one is pointing here. What is it? High to what? Low. This one is pointing here. It's what? Low to what? High. This one. Low to high, high to low. This one. Low to high, low to high. Did you get this or not? I said you can do different types of what? Different types of cascading. Cascading L matches, cascading T matches, cascading pi matches. I will show you an example in just a second. Clear? Okay. What was the problem with this? The problem with this is that it does not give you any degree of what? Freedom. What we refer to as what? Degree of freedom. Usually, I need you to understand one thing. Usually, the RP and the RS, look at this one. This example, numerical example. What was the RP? 50. What is the RS? 5. The transformation ratio is defined as what? The impedance that you want to what? Transform to. Clear? Usually, it's not large. What is 50 divided by 5? 10. Which means the Q is relatively what? Low, small. Do you agree with me or not? What is the Q in this case? In this case, in this example, the Q is what? Almost what? Roughly what? Roughly 3. Is it roughly 3? No, it's exactly 3. I'm sorry. It's exactly 3. Why? 50 over 10. 50 over 5 minus 1 is a 3. Is that a high Q or a low Q? This is a relatively low Q. And you have no control over it. Because you are going to get what? You are going, oh, one more thing. Aside. I don't know. I keep receiving that question. I thought you already know that. What is the definition of the Q? This is SI, quality factor. Anybody? Anybody? Quality factor of an RLC? Let's say series. Doesn't matter, series or parallel. Anybody? Definition. It's omega naught times what? The energy saved or stored, if you would like, energy stored in the circuit, divided by what? The average dissipated power. Of course, the dissipation of the power is through who? It's through R. Yes? Average. Average means what? So you need to take the what? You need to take sine. So the root means square. Okay, let me show you very quickly. For example, you can do the rest your own. It's just straightforward. For example, suppose we do have what? A series RLC. Okay, what is the energy? Let's assume that we are dealing with the electrical energy rather than what? Magnetic energy. Magnetic energy, you use what? Inductor. Yes? Electrical energy, you use what? The capacitor. Let's assume that we want to calculate the electrical energy. What is the energy? Energy stored quickly in C is equal to what? The integral from, let's say this is voltage here, V, is the integral from what? Of what? Vc of t times what? Ic of t dt. Did you get this or not? Vc is the voltage across the capacitor. It is the voltage, It is the current through the capacitor, and then what? dt. That's not power, that's energy. Yes? Which is equal to what? Which is equal to integral Vc of t. What is the I? What is the I? Is C dVc dt. dt. Agree? Yes or no? Okay. I'm sure you know this all, but I received a couple of emails about this. Okay, can I cancel this with this? Yes. So what do I have? I have C Vc of t dVc of t, which is what? Which is 1/2 C Vc square. Let's assume this is from 0 to Vc, whatever the maximum value. Yes or no? Okay. What is the power dissipated? Is what? It's at resonance. At resonance. What is the power dissipated at resonance? V, just V square. What is the power dissipated at resonance? 1/2 V square over what? R. Why is this V square? Why is it V square? Why is it V square? The voltage. At resonance. At resonance. What is this? Short. This is series circuit. So now what do we have? We have omega naught times what? Help me. 1/2 C Vc square divided by what? 1/2 V square over what? R, which is equal to what? Omega naught RC. That's a Q for the series. Yeah, by the way, for the inductor, you can do the same thing. And instead of what? And instead of substituting for the V, you put what? You put L di of t dt. Did you get this or not? Same thing. You will get what? Or it's equal to what? Omega naught L over what? R. Same idea. Clear? Okay, good. Now, let's get back to here. Okay, so now what do we have? We have the we have the L shape. I want to what? I want to transform from what? From from RP, which is a high impedance, a high resistance, to a what? To a lower impedance, which is what? RS. The L is what? The L is in this side, shaping this side. Clear? Okay. Now, what are the equations? This, by the way, I'm going to use what? All the equations that we derived this from the previous set of charts. This needs to be with you in the midterm. This, but don't make a copy of it. Just to bring it. But make sure that it's clear. It's not clear. But what I'm saying is that if you want to rewrite it again on a piece of paper, that's fine. Clear? Okay, good. Now, these are the equations. What is given in the problem? What will be given in the problem? RP and RS. That's it. Okay. So from here you are stuck with the value of what? Q. And from the Q you can find what? You can find all of these impedances of the capacitor and the inductor. Now what is it? You put first of all a component in what? In parallel. Whether it's what? Capacitor or whether it's what? Inductor. You can do both. Clear? Then you change the what? You change the parallel combination to what? Series combination. You follow me or not? Then you add what? You add a series. There is a typo here. This minus. You add a what? You add a series component, yes, with the what? With the opposite sign to cancel what? To cancel this, and you end up with what? You end up with just a series resistance. Then you go and what? Sketch the circuit all over again, which is what? This, and then what? This guy. Not this guy. This guy. Here. Clear? And again, as I told you, if this is J, this is what? Minus J, which means what? If this is a capacitor, this is a what? An inductor, and vice versa. Clear? Clear? Did we go over the example last time? Yes. Okay, this is a numerical example, you can see. And again, as I told you, whether you use this or whether you use that depends on what? Depends on the application, whether you want a high pass, whether you want AC coupling, or whether you want what? DC coupling. If you want AC coupling, which one do you use? You use the high pass filter. Are you following me? If you use DC coupling, then you use the what? The low pass filter. DC coupling means what? You want the DC to pass. Did you get this or not? Okay. Clear? Okay. A problem in this in the midterm, you will see it in the cookie section. Cookie means what? Just to plug in, but you need to know which equation to plug in and what to plug in. Did you get this or not? Okay, good. Now, and then we took another example in which what? In which we want to go from what? A low resistance to a what? A high resistance. In here, and instead, see, in here, what did we do? We added one in what? In parallel. In here, what do we add? One in series and change it to what? Parallel. And then you add another parallel such that the admittance is what? Cancels out. Admittances add, which means what? They cancel out. Yes? And then what? And then the circuit behaves what? This. What did I do? This one. Yes? And you add this, the one, this is the parallel here. Clear? And the equations, again, the same idea, which is what? A single degree, sorry, no degrees of what? Freedom. The RP and RS is already given. What I would like to have is what? Is one type of a circuit that I can delineate. Delineate means what? Separate. The what? The Q from the what? From the RP and the what? And the RS. So that I have multiple what? Multiple degrees of freedom. Did you get this or not? You can do that through the use of what? Through the use of different types of what? Cascaded L or what? The T match or the what? Or the pi match and so on and so forth. Clear? Let's take an example. Let's take an example. Omit this one, let me use a pen. Suppose I have an example. Suppose I have a resistance. Let's call this one RP. Okay. And then what am I going to use? Let's see if you can help me. Where am I going here? Just here. Where am I going? High to what? Low. Why? Because this one is pointing this way. Yes or no? Okay. And let's assume this is what? R sub I. Yes? What is the I stands for? Intermediate. Intermediate. This is, by the way, this is not the goal. This is not the goal. Clear? Okay. This is L2 and this is what? C2. Yes? This is an L shape. And from here, I have another L shape like this. Did you get it or not? This is what? C1 and this is what? Help me. L1. And what do I want? I want this to be what? To be, let's say, RS or RG, whatever you want to call it. Did you get my point or not? Okay, now, let me ask you a question. What is the resistance here, looking at this side? The resistance looking this side should be the same as what? The resistance looking this side. So this one is what? RI. Did you get this or not? This one is going to what? Change it from what? High to what? Low. This one is from where? Low to what? High. Did you get this or not? Okay, now you might say, but if it is high or different values. Did you get this or not? Okay, let's see if you can help me. What do I do? What do I do? How do you analyze this circuit? Okay, first of all, can you change this into series? This one, this one. Can you change it into a series? Using what? Using this equation. So what do I have? Let's see if you can help me. This is now what? What is this? This is CS. Sorry, Yeah, CS. This is what? This is a capacitor in parallel. It will become what? Series. But the values, this one and this one, are very close to what? To each other. Yes or no? What will this one be? This is RS. Did you get this? No, RS I use here. 1 second. Let me use this one RN. G. Sorry, RG. Let me use this one RG so that we don't get confused. This one is RS is the what? Is the series. Yes? And this is the what? L2. Now, what is the impedance look? Oh, sorry, what is this looking at this? This is what? RI. Yes? Okay. Don't worry about the other side. We'll get to the other side in a minute. What is the Q? I'm going to call it what? Q right. Q right means what? This is a right circuit. Yes or no? Yeah. Right does not mean correct. Means to your right. Oh, what is it? Give it to me. Now, it's a series circuit. You can use either the inductor or what? Capacitor. I'm going to use the inductor. So what is it? Omega naught L2 over what? Over R? Over R. Clear? Clear so far? Yes or no? Because the impedance looking in here is equal to what? Rn. Yes or no? At resonance, by the way, at resonance, what will this one and this one do? Cancel each other. Yes or no? So the Rn will be the same as this Rs. Did you get my point or not? Okay. Which is equal to what? What is it equal from this equation? The square root is what? Square root of what? Rp over what? Rn minus 1. Did you lose me? Did you lose me? This is not the Q of the overall circuit. This is the Q of only what? This side. Clear? Okay. Now, add the other side. What do I have? What is this one here looking into? What is this resistance looking into? Ri? Yes or no? And this the resistance looking this way is what? Rg. Tell me. Q left. Still waiting. It's omega naught. L what? 1. Yes? Over what? Ri? Yes or no? Equal to? Give it to me. Rg over what? Ri minus 1. This is equation 2. Clear? Help me now. What is the overall Q? Overall Q is what? Omega naught L1 plus what? Omega naught L2. Why am I adding? Why am I adding? Because this, oops, sorry. This one and this one are in what? Series. Yes or no? Divided by what? Divided by Ri, which is equal to what? Q, right? Plus what? Left. Did you get this or not? Cannot hear you. No response. Okay, so now tell me, how many degrees of freedom do I have? What do you mean 1? I have L1 here. Yes or no? I can use L2 to decide on what? What is the total Q? See this one? This one is only going to tell me what is the what? Q right, and what is the what? Q left. And the Ri, you choose it. Do you follow me or not? In other words, is the Ri given? Ri is not given. You choose it such that you get the desired what? The desired bandwidth, or the desired omega naught, or the desired Q, and so on and so forth. In addition, you are going to have what? L1 and L2 in here also to determine the overall Q. Clear? So, from the Ri, what are you going to get? The question gives you only what? Rp and what? Rg. Yes? So, you choose the Ri, what is it from it? You are going to get what? The Q right and the what? Q left. Did you get this or not? Using which equation? This equation, not this. This one you cannot use it. Why? You don't know what the L1 and the L2 is. Yes or no? Yes. Okay, so once you get these, then you can get what? L1 and L2, and then it will control the value of what? Of the overall Q. Clear? Yeah.
Is the main motivation here just to have more freedom?
That's more freedom. More freedom to decide, to come up with a design that, first of all, is a practical design. You are not going to get values which are what? Out of the ordinary. Out of the ordinary means what? By the way, once you get to the values of the Q, you can also find the capacitance. You agree? Yes. Yes or no? Okay. You get the values which are what? Reasonable, that is available in the library, for example, in the lab. You understand that or not? Different values of Q, different values of resonance frequency, and so on. So you don't want to be stuck with what equation, one equation that will decide everything.
The only disadvantage is adding complexity to the...
This you are adding 2L. So if they are what? If they are going to provide for insertion losses, you are going to get what? Double insertion losses. That's the price you pay. Clear? Yeah.
For the overall Q, why is it RI and not RI?
The question is for the overall Q. Why is this one RI? The impedance looking at here and the impedance looking at here, the resistance, I mean, is the same. It's RI. It's the same. You follow me? In other words, at resonance, what is RI equal to? RS. Are you following me on that? Yes or no? So it's whether you take this or whether you take this, it's the same thing.
So you're like looking at the middle.
The middle. Yeah, rather than each side. Yes. But this resistance and this resistance is the same. Clear? Now, extra credit for you. Extra credit. Let's see how many of you participate in this. There is a lot of examples in here. Of course, I'm not going to go over each one of them. I just went over one of them. Do you understand or not? What I want you to do is to pick one of them. Pick one of them and generate these equations. Do you understand what I just said or not? Did you get this or not? Pick. You see how many choices you have. This. Did you get this or not? What is this, by the way? What is this? This is L back to back. Not facing each other, but facing like this. You get a what? A T. Did you get this or not? Pick one of them. By the way, if you can pick two, it's better, but you don't get extra cut. Pick one of them, and no, not this one, not this one. And generate the equations. In other words, prove the equations like I just did. You follow me or not? And email it to me for 1 point. 1 point extra credit, and the deadline is Sunday midnight. Did you understand it? Or do I need to write it down? I don't need to write it down. So one more time. Pick any one of these. Pick any one of these. Yes? See, because once you pick one of them and you are able to derive the equations, I will feel good that you will be able to what? To derive any other equations. Yes? Now, all of these equations will be in your 8 by 11. Do you understand? I'm not going to ask you in the exam to derive this equation. Yes? But I want to make sure that you know how to derive it. Yes? Pick one for 1 extra credit. Sunday night. Sunday night, it means what? 11:59. 11:59 what? Sorry. 11:59 p.m. Yes. Okay. Now, this one I will skip. Why? Because I need to introduce it first of all to the what? To the transmission line, and then we come back to see how the transmission line by itself can be used as a what? As a matching circuit. Clear? So this one to be what? To be reviewed shortly. In about half an hour. So, clear? Okay, good. Now, let's get into the transmission line. Now, in here, I have prepared, it's for some reason, today in the office there was not too much activity. So I made the notes so that we don't go over this. And this one, the notes is not very clear. I need you, first of all, to understand the basic idea, first of all, before we get into the analysis. I don't want you to write anything. This, very nice handwriting. You agree or you do not agree? By the way, if you don't agree, watch the handwriting of other professors and then what? Make a comment. How many of you are taking course with Professor Molish? Handwriting? Like this? No way. So, we'll get to it. But I need, first of all, to justify to you why do we study the transmission lines. In lump circuits, in circuit analysis, the courses that we took earlier when we were young about what? LRC, Kirchhoff's voltage law, Kirchhoff's current law, and so on and so forth. They were all what? They were all used for what? Low frequencies. Are you following me or not? What we were saying is that if I have in a circuit, let's assume that I have in a circuit like this, and then what here? Another component. Answer me the following question. Is the voltage here the same as the voltage here? The same as the voltage here. But we discover that if we put here, and this one, a transmission line, and we increase the frequencies to the RF, this voltage and this voltage will not be the same. Do you understand that or not? Which means, what does that tell you? It tells you that at low what? At very high frequencies. At very high frequencies, what does it mean? It means the lambda is what? Small, very small. Are you following me? Very small. We will see that we cannot use the what? The lumped circuit analysis. We need to study what is known as what? Distributed analysis. Did you understand? Distributed over the length of the what? Of the telephone line. Yes or no? However, if we take an infinitesimal portion of the telephone line or of the transmission line, infinitesimal, delta X, can I use the lump theory? I can use the lump theory. Why? Because the size of the circuit will be comparable to the what? To the low lambda. Did you get my point or not? Yes or no? That's the whole idea. So now, let's get to the, see if you can read the charts on your own. Let's see if you can help me here. This, don't write anything, just listen to me. 1 second. Okay, what do I have here? That's the transmission line. Yes? What is the length? Delta X, where delta X will approach what? 0, which means I am taking a what? An infinitesimal length of the transmission line. Yes? Okay, now what do I have? Let's assume this is the origin. Yes? So what do I have? In here, the voltage is what? V of X comma what? T. In here, the voltage will not be V of what? X comma T. Did you understand that or not? Okay. The current is what? I of X comma T. Clear so far? How am I going to model this telephone line or this transmission line? How am I going to model it? I'm going to model it by what? A resistance in series with a what? Inductor, a capacitor in what? In parallel, and a what? Conductance in parallel as well. The resistance is due to the what? Conductance of the transmission line. The inductor is through what? The self-induction. Are you following me? The capacitor is because what? We do have two lines that are running what? Parallel to each other. They behave as a what? As a capacitor, two plates. Did you get this or not? And this is the conductance of what? Some dielectric between those lines. Clear? No response. Every one of them is multiplied by what? Delta X. Which means, what is the unit of R? This R, it's ohm per unit what? Meter, for example. Did you understand that or not? So that when you multiply it by meters, it becomes what? Just what? Ohm. This one is what? Henry per what? Meter. This one is what? Farad per what? Meter. This one is what? Mo. Mo means what? 1 over ohm. Mo. Mo per meter. Did you get this on that? Ohm inverse of ohm is what? Is mo. Yes? Okay. Now, can we write now the Kirchhoff's voltage law and the Kirchhoff's current law? Why? Because we are looking at an infinitesimal segment of the what? By the way, the transmission line is what? Is these repeated many, many times. Did you get this or not? Oh, by the way, this is the model for a telephone line. If you are modeling the telephone line as a what? As a narrowband channel transmitting over a telephone line, yes, this is the model of a telephone line. Oh, so now help me with the equation. This voltage is what? Vx of t. This one is what? Vx plus delta x. Because this one is what? Is delta x here. So it's Vx plus delta x comma what? T. Same thing with the current. This, oops, missing. This is I x t. What is this current? I x plus delta xt. Are they equal? They are not equal because there will be some current coming in here. Yes or no? Okay, good. Let's see if you can help me. Kirchhoff's law, voltage law. What is it? This voltage, Vx of t, minus this voltage is equal to what? R delta x times what? The current. That's the voltage drop. Plus what? L delta x di of c dt. That's the voltage drop across the conductor. Yes or no? Did you lose me? Okay. Now, divide by delta x and let delta x approaches what? 0. So what do you get? You get partial. Why partial? Why partial? Because the voltage depends on both The time and the what? The distance. So I am differentiating here with respect to what? With respect to the distance. Clear? So dbx, partial b, partial x. Why is this minus? Tell me why is this now minus? No response. The derivative is what? Is this minus this? Not this minus this. Yes? So if you bring this one to this side and bring this one to the side, bring this one becomes minus. Clear? Did you get this or not? Okay. Why is this one partial t? Partial t because this is partial t here. What happened to the delta x's? These delta x's. I'd say I'm dividing by delta x and letting delta x approaches here. Question number 1. By the way, look at how many equations we have. 28. You will have a lot of equations to write in your 8 by 11. You will have more than one 8 by 11. So don't worry about that. Did you understand equation 1? I don't want you to get bogged down. Sorry, I don't want you to bog me down with Kirchhoff's equations. This is straightforward. Yes.
I couldn't understand why we put Rx, R in terms of the R delta X.
This is a what? Resistance per unit meter. If you increase the length, the resistance will increase. This is just the resistance per unit what? Per unit distance. So as you increase the distance, the resistance will also what? Increase.
So if I multiply this with the length of the wire, I will end up with the resistance of the wire.
That's true. But I'm only looking at what? Just a small infinitesimal, which is what? Resistance of that small infinitesimal. Okay. Now, Kirchhoff's current law. KCL stands for what? Kirchhoff's current law. Clear? Okay. Help me. What do I do? Help me. I x of t minus I x of plus delta x t will be equal to what? The current here plus the current here. Yes or no? What is the current here? The current here. Minus, sorry, before the minus. G delta x, this G delta x times the voltage, which is what? Vx plus delta x comma t, plus what? What is this? This is the current through the capacitor, which is what? C delta x partial V x plus delta x comma t divided by with respect to what? T. Did you get it? Yes or no? And again, divide by delta x, bring this one to this side, is what? Partial I, partial x, equal to what? Minus G. What happened to this? Why is it this? Why is it V of x of t? It's because delta x approaches what? Approaches 0. So Vx of t minus C dBx dt. Clear? Did you understand these two equations? Because this is where it's going to start getting me the rest of the equation. Clear? Okay. Both of these equations, equation 1 and equation 2, represent what? The time domain analysis. Yes? If I take the phasor analysis, I end up with what? I end up with the equations in terms of what? In the frequency domain. Yes? So what is it? Let's see. In the phasor analysis, what is Vx of t? Is the real value of what? V capital V. Now it's capital V. Vx e to the j omega t. Same thing with the current. Yes? So if I substitute in 1 and 2, it becomes like this. dVx. You notice, by the way, it's no longer partial derivative. Why? Why is it no longer partial derivative? Don't write anything. I just told you I saw you writing. Yeah. Do not write. You can download it. Okay. Why is it not partial derivative? It's because this one is in what? In the phasor domain. Time does not get into there. Yes? So what is it? dVx dx equal to what? Minus R j omega L. What is j omega L? That's the impedance of the inductor. Yes? Why is it minus? Why is it minus? Because there is already a minus sign in here. Yes or no? So it's minus R plus j omega L Ix. And this one is what? Minus j plus j omega c Vx. Clear? Now, differentiate equation 3 with respect to x again. With respect to x again, what will this side become? This second derivative of Vx. Yes or no? Yes. What will this one be? Dix dx, which means what? I'm going to substitute this. So what do I get? Minus R plus j omega L times what? What happened? Minus minus is plus. Why is it? Because I brought it to this side. I brought it to this side. Yes? So it's what? Minus G plus J omega C times what? Times V. Did you answer where this Vx came from? This, when I differentiate with respect to X, I substitute this. I ended up with this equation. What is this equation? Have we seen this equation before? This is a second order differential equation. So let's simple. By the way, the same thing with the current. In the current, what do? I differentiate this with respect to who? X, and instead of dV dx, I will use this equation. Did you get this or not? Am I going too fast, or you are following me? Are you following me? Okay, good. Now, so I get these two equations. Now let's define this. R plus J omega L, G plus J omega C, the whole thing square root. Let's call it what? Gamma. Gamma is called the what? The propagation constant. The propagation constant. In general, it's a what? It is a complex number. Why? Because there is a complex functions here. Yes? Which means what? You can write it as alpha plus what? J beta. Alpha is the attenuation constant. Attenuation in terms of what? The magnitude. And the beta is in terms of what? In terms of the phase. Clear? Now we will see shortly that beta is what? Is 2 pi over what? Lambda. Lambda being what? The wavelength. Clear? Let's not worry about that. We'll get to it in a minute. Are you following me so far or not? Yes or no? Okay, good. We are almost there. Almost there. So what do I have? What do I have here? It will become what? Part. In other words, this is how I get it. Huh? What is this? A gamma square times what? VF, this minus equal to what? 0. Huh?
We cannot see it.
I cannot what?
We cannot see it.
Here. Anybody knows what this equation is called? This differential equation? When you do have the second derivative? Anybody? 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 This Laplace equation. They call it the Laplace equation. Anyway, don't worry about it. Don't worry about it. Can you tell me what is the solution? What is the solution of this differential equation? The differential equation is what? Some constant times what? E to the what? Yes? Plus another constant. E to the what? Gamma x. Did you understand that or not? Why do I get two roots? The roots are what? Plus or minus what? Gamma. Yes or no? You forgot about this? Quickly, let me remind you quickly. What is the operator? Second derivative. Yes? So you get what? D square minus 1, D the operator. Yes or no? Times what? V of x equal to 0. What are the roots? This is called the characteristic. I cannot believe I'm teaching this. This is called the what? The characteristic polynomial. Yes? What are the roots? Plus or minus what? Plus or minus 1. Are they real? The roots, are they distinct? Then the roots will be what? They will be like this. Because if they are what? Repeated roots, this one will be what? A x times what? E to the gamma x. But it's real roots. Plus or minus 1. It's plus or minus 1. Yes? This is the solution. Let's see the notation. Get familiar with the notation. What is this? A moment ago, what did I write it? As A. Yes? In here I'm going to write it what? VO plus E to the minus gamma x. Remember, gamma is what? In general, complex. Yes or no? No response. Yes. Okay. A V naught plus E to the minus gamma x plus what? V naught minus E to the gamma x. Clear? What is this in words? In words, what is this? This is the voltage on the line at any point. This is the voltage on the line at any point. In other words, once you plug in the value of x, let's assume that you took this as what? You took this as a reference x equal to 0. If you plug in the values of any x, this is the voltage on the line, consisting of how many components? 2 components. One of them is called the incident, which is in which direction? This direction, forward direction, and the other one is called the what? The reflected, which is in the what? In the other direction. Did you get this or not? So in every point on the transmission line, we are going to have what is known as what? Two waveforms. The sum of them is what is known as the standing waveform. Yes or no? Did you take this in any other class? Which one? Undergrad back home, you mean?
Yes.
Okay, so this bringing memory? Pleasant memory or not pleasant? Okay. People usually don't like transmission lines and microwave and stuff, but we are stuck with it. We need to understand it. So you have no other choice. And you will see this in the midterm. Clear? Okay, so let's understand. Okay, so it's V naught plus. It's same thing with the current. This is a wave of propagation in the direction of what? The positive x-axis. This one is propagating in the what? In the negative x-axis. Clear? Clear? Okay, good. Now, if I differentiate equation what? 7. With respect to what? With respect to x. This equation. If I differentiate it with respect to x, and I substituted in equation what? 3. Yes? You lost me here. Concentrate. If I differentiate this with respect to what? X. Which means what is this side? ddx, dx. And I substituted in here, I get this relation. I get. What do I get? I get I of x. Yes? Where is this I of x coming from? Where is this I of x coming from? This is this I of x. I get I of x is this. And then I compare this I of x to this I of x. What can you tell me? What can you tell me? Look at this and look at this. E to the minus gamma x is e to the minus gamma x. Which means what? What is I0 plus? I0 plus is what? Is V0 plus times what? Gamma divided by what? R plus j omega L. Yes or no? Cannot hear you. This became negative. Yes? No response. This one became negative. Yes? Why is it negative? Because it's in the opposite direction. Current is in the opposite direction. Yes or no?
Yes.
Okay. So it's this. Now we define another thing. Define Z naught, which is called what? The characteristic impedance of the transmission line. Question. This is a real impedance or not a real impedance? That's not a real impedance. Are you following that? It's not a real impedance. In other words, it's not an impedance that you go and pick it up from what? From the lab. Clear? This is just a definition. Yes or no? Okay. What is it? So that the reason I put it this way, so that this equation become what? I of x equal to what? V naught plus divided by Z naught. Yes or no? Times what? E to the minus gamma x minus V naught minus Z naught e to the gamma x. Clear so far? Yes or no? Okay. Now, what is the gamma? What is the gamma? The gamma is the gamma is the square root of R plus J omega L times what? G plus J omega C, the whole thing what? Square root. Which means the Z naught, first of all, did you understand this? Yes or no? Yes. Okay. Which means what? The Z naught is equal to what? What is the Z naught? Help me. What is the gamma? One more time. It's this. So it will be what? The square root of what? R plus J omega L divided by what? The square root of G plus J omega C. Did you lose me? Did you lose me? No response. Did you lose me? This gamma is what? R plus J omega L over what? This Z naught. R plus J omega L over gamma. This gamma is this. So this, you have only this and this. Clear? Now, we are going to deal with only one case in this semester. That's all what we need. Which is what? Which is the case of a lossless transmission line. What does a lossless transmission line means? It means what? It means, first of all, R equal to G equal to what? 0. There is no resistance. There is no what? Conductance. Are you following? There is no power losses. Did you get this or not? Yes. Okay. So what do I have? The R and the G are what? Zeros. Yes? And what do I end up with? The j omega, of course, cancel with the j omega. Yes? What do I end up with? I end up with z naught equal to what? Square root of what? L over what? C. Clear? That is referred, by the way, is it a real number? That is a real number. Usually it is how much? Usually we use it as what? As 50 ohm. For some cables, they are what? 75 ohms and so on so. Let's not worry about that. The question will give it to you. Did you get my point on that? This is the real, this is case. By the way, I said case one, remove. There is only one case. There is no case one. There's only one case. So what is the equation? Tell me what is the equation now become? This is the major equation. This is the major equation. Unbelievable, I did not put a number here. But this is the one that we build upon. Vx, which is what? One more time. What is Vx? Vx is the voltage on the line at any point x. Clear? Okay. Equal to what? V naught plus. V naught plus. Why is this one now e to the minus j beta x? Because alpha is equal to what? 0. So the gamma is what? Purely imaginary. So it's what? V naught plus e to the minus j beta x plus what? V naught minus e to the j beta x. And this one, same thing, divide by z naught, but this one is what? It's negative. Clear? Clear so far? No response. Okay. Now, let's start looking at situations, which is what? Termination of the transmission line, both at the load and at what? At the source, to see what happens. Are you following me on that? At the beginning, we are going to assume that the transmission line is matched to the what? Source. Which means what? I will not have any reflections on the what? On the source. Or concentrate on the load. Yes? So I have, this is the line. Now, change in strategy. Instead, not strategy, sorry. In what strategy? In convention. In here, what did I assume? I took this as a 0. I took this as a 0, and the positive x-axis was this way. Yes? In here, I'm going to assume the load is at x equal to 0, and when I say L, it means that when I'm looking at the input to the transmission line, what is the x? Negative L. Did you understand what I just said or not? Yes or no? It's just a matter of notation, because right now I'm concentrating on the what? On the load. Clear? Okay. Now, before I continue with this, let me ask a question. Let's see if you can answer. Can we measure V0 plus? This V0 plus, can I measure it? Measure it means what? Can I bring a voltmeter or whatever to measure this voltage? I cannot do that. This is what? This is the result of the solutions of the differential equation. Did you get this or not? So somehow I need to get rid of these, the V0 plus and the V0 minus. Did you get this? In place of it, what do I need? I need to replace them by the what? By the voltage, for example, at the generator, or the voltage at the load, and so on. So think that I can actually measure. Clear? Can I measure this? V of x, I can measure the voltage on any point in the line. But this one, I cannot measure it. Clear? Okay, good. Now, let's see if you can help me. I put a load, and the load is what? ZL, which is not equal to what? Z naught. Yes? Now remember, Z naught, the transmission line is described by what now? How are you describing the transmission line? You are describing the line by its length, which is L, by its characteristic impedance, which is what? Z naught, and by the what? The phase constant, which is beta. It's not gamma because the alpha is equal to 0, just beta. Did you get this or not? And remember, as I will show you shortly, the beta is actually what? 2 pi over what? Lambda, which means you are specifying the line by its what? Length. You will hear people talking about this. I want you to get familiar with this. They call it what? A quarter of a wavelength transmission line. What does that mean? It means L is equal to what? Lambda over 4. Did you get my point? This is how they call it. A quarter of a wavelength transmission line. It means L is equal to what? Lambda over 4. Or 1/2 lambda over 2. Did you get this or not? Okay, good. Now, let's see if you can help me. The ratio of the voltage to the current at the load must be equal to what? ZL. Remember, what did we say here? What are these? These are the voltages at where? At any point. Now, in this case, what is the X? 0. The voltage at X equal to 0, when you divide by the current at X equal to 0, you should get the value of what? ZL. That's Ohm's law. Did you get my point on that? No response. So what do I have? I put 0, plug in X equal to 0. What is the voltage? V0 plus what? V0 minus divided by what? V0 plus minus V0 minus. Yes? Where did this come from? This, you know, there is a 0 here, it comes in the numerator. Yes or no? Okay. From this equation, what do I find? I find that V0 minus is equal to what? This term, which is what? ZL minus Z naught. One more time. What is V0 plus? Incident voltage. What is the V0 minus? Reflected voltage. What do I get? Excuse me. What do I get? V0 minus equal to what? ZL minus Z naught over ZL plus Z naught, V0 plus. Do you answer where this equation came from, or do you want me to show it to you? This equation from here, you find what? V0 minus in terms of the remaining one. Yes? We are going to define this parameter, which is what? ZL minus Z naught divided by what? ZL plus Z naught, yes? As a what? As gamma L. Did you understand that? This is the capital gamma, if you will like. Yes or no? Gamma sub L, which is called what? The voltage reflection coefficient. The voltage reflection coefficient at where? At the load. Where are we looking into? Please tell me the source. Where are we looking into? We are looking into the what? Into the load. Where is the source here? The source is on this side. Did you get this or not? I'm looking into the what? Into the load. Did you get this or not? That's a reflection coefficient. Clear? Cases. Let's see if you can help me. If ZL is equal to Z naught, if ZL equal to Z naught, what do I say first of all? What do I say? I say the load is matched to the line. Did you get this or not? The load is matched to the line. What will happen? Gamma will be, Gamma L will be equal to what? 0, which means there is no reflection. Good or bad? That is good. Are you following or not? Good. There is no reflection. Clear? Okay. We will see that if there is no reflection, when we talk about power, our interest is not in the voltages. Our interest is in the power. When we see if there is no reflection, then the incident power will be the same as the transmitted power. I want you to understand it like this way. There is a barrier here. This is the load. The power, this power is called what? The incident power. What is this? This is PT, which is the power transmitted. This is the what? The reflected power. So if the power reflected, if there is no reflection, this one will be the same as this one. Clear? Okay. Now, another note. ZL may be what? Complex. Now, we already know that Z naught for a lossless line is what? Is real. But could ZL be constant? Sorry, I said constant. Could ZL be complex? By the way, most of the time ZL will be complex. Remember what I told you last time? When you look at the input of a common source amplifier, the impedance is highly what? Highly capacitive. So it will be complex. If it's complex, what does that tell you? It tells you gamma L is in general what? Complex. Did you get this or not? What does that tell you? It tells you that once we get to the equations of the power, you will not see gamma L by itself. You will see the what? Magnitude of gamma L. Did you get this or not? You are not going to see gamma L by itself. You will see what? Magnitude of gamma L in the equations. I will show you that when we get there in a minute. Clear? Yes or no?
Yes.
Clear? Okay, good. Now, so now what do I have? The total voltage and current on the line at any point. Now, how am I going to modify the equations? I'm going to modify the equations as what? V0 plus e to the minus jbx plus what? And instead of the V0 minus, what am I going to write? What is the V0 minus? I think I skipped one equation. What is the V0 minus? V0 minus is what? It's gamma L divided by times what? V0 plus. Yes or no? Okay, good. So it's V0 plus e to the minus j beta x plus what? Gamma L times what? E to the j beta x, and the same thing with the ix. Same equation, except for this one is plus. This one becomes what? Minus, and the V0 plus is divided by what? C0. Clear? And what do you notice one more time? You notice that the voltage and the current consist of two components. Two components. The incident component and the what? Reflected component. And the superposition of the incident and the reflected excuse me, is what is referred to as what? Distant waves. Now, one parameter that I need to introduce you before we get to the impedance issues, which is the following. These are important parameters that are given in spec or whatever. The first one is called what? The return loss. I don't want you to forget this. This is called what? RL. RL in the, let me show it to you, this one in the chart, so that if you are reading the chart, this is this one. By the way, notice the insertion loss and the return loss all depends on what? All depends on the value of what? Gamma. Did you get it? I said gamma. Yeah, capital gamma. Yes? Okay. I will make a comment on this in just a second. Help me. So it's what? Minus 20 log absolute value of what? Gamma. Now, if the absolute value of gamma is equal to what? 0. What does it mean? What does it mean when I say absolute value of gamma is equal to 0? No reflection. It's a matching case. What is the RL? The return loss. Minus infinity dB. Are you following me? Minus infinity dB is what? Minus 20 log of 0. When gamma L is equal, sorry, I said gamma L. Absolute value of gamma L equal to what? 1. Let's go back to the gamma L. This is the gamma L. Yes? Yes? When will the absolute value of gamma L equal to 1? When ZL equal to what? 0, which means what? A short circuit. Yes or no? Or ZL equal to what? Infinity. Do you understand why ZL equal to infinity? This one will also still be equal to 1? Yes or no? If ZL equal to 0, what is it? It's minus 1. But when you take the absolute, when you deal with power, you take absolute value. Yes or no? Okay. So when ZL, in other words, either what? Either the load is open circuit or what? Short circuit. Now you might say, why am I putting a short circuit at the load or what? An open circuit at the load. We will see when we get to the use of the transmission line as a what? As a matching circuit. Do you understand that? As a matching circuit. We'll get to it. Clear? You can do, by the way, you can use the transmission line if you don't have a given inductor or a what? A given capacitor. In other words, if you need a value for a capacitor or an inductor, but you don't have that value, you can replace it by a what? A transmission line that is either what? Short circuit loading, or what? Open circuit loading. Clear? We'll get to those in just a second. Yes.
Is it possible that Z0 equals 0?
Z0 we just calculated equal to what? The square root of what? L over C. So what do you mean that it's equal to 0? Don't look at an equation. Just don't look at just the equation. Z0 is equal to what? Where is it? Where is it? I have no idea where I put it. Here. Z0 equal to square root of L over C. Now remember, we already put R equal to G equal to 0. Yes? Now you are telling me put L and C also equal to 0. So what do you have left? Nothing. Clear? Okay, good. Now, let's understand the other parameter. This one is even more important than the other one, which is called what? The voltage standing wave ratio. Abbreviation of it is VSWR. They expect you to know this in the RF industry. However, sometimes they drop the V, so they just call it what? The standing wave ratio. Clear? I need you to understand what does this mean. Equation 17, this equation. This equation, tell me what is the magnitude of Vx, the magnitude. The magnitude of Vx is the magnitude of this guy, yes, times the what? The magnitude of this. Now, I want you to see what I did here. Can I factor this outside? E to the minus j beta x. What will this one become? E to the j 2 beta x. Yes? What is the magnitude of e to the minus j beta x? It's 1. That's a complex exponential. So did you understand this equation? Where is it? Did you understand this equation? Yes or no? Okay. And what is this equal to? This is equal to the absolute value of what? V0 plus times what? 1 plus. The gamma is in general what? Complex. Which means what? You can write it as a what? As a magnitude times what? The phase. So what is this theta? That theta is the phase of what? Of the gamma L. Did you get this or not? Yes or no? Okay. This is the voltage. What do you notice in here? You notice in here that the voltage magnitude on the line is what? Oscillating. Why? Where is the term that shows the oscillation? This term. You follow me or not? Whereas in the lump circuit, if we do have a line, then the voltage will not be what? Oscillating. It will be the same value. If I have like this, a circuit like this, and I tell you what is the voltage here, what is the voltage here, you tell me that what? The voltage is the same. Yes? In here, no, the voltage is what? It's oscillating. What is the maximum value? What is the maximum value? Amplitude or magnitude, if you'd like. The maximum value is when this one is equal to what? 2 pi or what? Multiple of 2 pi's. Did you get this or not? Integer multiples of 2 pi. Agree? What will its value be? 1, which means this one is like this. Clear? Okay. What is the minimum value? What is the minimum amplitude? The minimum amplitude is when this angle is equal to what? Is equal to multiple. No. What do you mean multiple of pi? Odd multiples of pi. Did you get this or not? Odd multiples of pi. Clear? Okay. It will be like this. Why? Because this one will be negative. Yes or no? The ratio between the maximum voltage, magnitude, divided by the minimum voltage, magnitude. Yes? Is what? Is what is referred to as what? The standing wave ratio. Clear? And what do you notice? The standing wave ratio is a what? Is a real number. Is a real number. Why? So we are taking magnitudes here. Clear? It's a real number. Now, what is the values ranges? What values can this one take? This value can take anywhere between what? 1 to infinity. When is it 1? When the absolute value of gamma L equal to what? 0. Which means what? Match. So the smaller the value of SWR, the standing wave ratio, the smaller the value, the better or the worse? The better. The larger the VSWR, it means what? It means, excuse me, it means that it will go to what? It will go to infinity. When will this one be equal to infinity? When this one equal to infinity? When the denominator equal to what? 0. But when will the denominator be equal to 0? When the absolute value of gamma L equal to what? 1. Which is a when? When the transmission line is either what? We did this a moment ago. Which is what? When the, no, where did we write it? I lost. When gamma L, it means what? The load is absolute value of gamma L equal to 1 is when the load is either what? Short circuit or what? Open circuit. Clear so far? Yes or no? Do not forget these two parameters, the return loss and the what? and the SWR, the standing wave ratio. These are crucial things, again, in the RF industry. They expect you to know it. Clear? Did you take this in some other class? Or this is the first time? Huh? It's in the undergrad? Okay. No, what I'm saying here. No? Okay, fine. Doesn't matter. Clear? Clear? Okay. Now, I want you to understand this very carefully. And this will show you why in this chart, if I can find it. You see this in this chart, it says what? Gamma N? Okay, I need to explain to you one thing here. The reflection coefficient can be calculated at any point. At any point. Why? Because we already know the equation. Where is the gamma L? The gamma. Where is the gamma? Which equation is this? This is the gamma L. Which is what? Or the gamma in general. It's what? It's Vx divided by what? Z is what? Vx over Ix. Yes? The gamma is what? Tell me here, what did I do? What did I substitute for the gamma? What did I substitute? X equal to what? Minus L. Which means where am I? At the source. Yes? What is it equal to? V naught minus e to the minus j beta L. Why is it now minus? The V naught minus is usually associated with what? With the positive. You lost me here? Huh? Because we substitute here. Yes? We substituted for x to be what? Minus L. So it's what? V naught minus e to the minus j beta L. V naught plus e to the j beta L. Yes? But what is V naught minus over V naught plus? It's gamma L. Did you get my point or not? This L is what? It's at the load. Did you get this or not? This is at where? We are looking into what? You lost me here. Which gamma? This one? This one? This one? Minus. Oh, sorry. Minus. Yes, you are right. Minus. Clear? I want you to tell me, what do you notice? What do you notice? It's written here. What do you notice? Is that the magnitude of the reflection coefficient is always what? The same, no matter where you are looking. Did you get my point or not? Yes or no? The magnitude, not the reflection coefficient. The reflection coefficient is not the same. But the magnitude of the reflection coefficient is what? The same, no matter where you are looking. Yes? Why? This is the equation. If you take the magnitude, what is the magnitude of this guy? 1. So you get the magnitude of this equal to the magnitude of this. So what I'm trying to tell you is that in the equation for the what? In the equation for insertion losses, when you see magnitude, that could be measured anywhere you want. Do you understand? It's the same value. Clear? Okay, good. Now, we'll get to the charts shortly. Now, are you following me so far or not? Am I going too fast or not? Too fast? Okay, good. Now, let's look now at the impedance. Let's look at the impedance, and that will tell us how we are going to use what? How we are going to use this as a what? As an impedance matching circuit or network. Did you get this or not? Okay. So I have the transmission line again. This is ZL. Notice, by the way, one more time. We are still assuming that the line is matched to who? To the source. We'll get to the other case in just a second. Clear? Okay. So I'm looking at what? I'm looking between these two ports. The source is where? Here. There is no reflection from the source because it's matched to the line. Clear? No response. Okay. I'm looking in here. What is this Cn? It must be the voltage in here divided by what? The current. Do we agree? Do we agree? Measured at what? V minus L divided by what? I minus L. Yes or no? What do I get? I use these equations with X equal to what? Minus L. So what do I get? V0 e to the minus j beta L, oops, e to the j beta L. Because when X is minus L, this one becomes positive. Yes? plus this divided by what? This. Yes? If you do that, this is what you end up with. By the way, do you understand where this came from? See? If you factor out the e to the j2 beta x, yes? When you divide this by this, it will cancel. Did you lose me? Did you lose me? Or you are saturated? Are you saturated? By the way, I don't care. If you are saturated or not saturated. I still have what? I still have minutes to go. Did you get this or not?
5
okay,
minutes
so
left, yeah.
saturated or no saturation? I don't care. Okay, now, did you understand this equation? Now, what do I do with this equation? Instead of gamma, I'm going to use equation what? 17. No, sorry, this one is got it from equation 17. Equation 16, which is this one. Instead of this gamma L, I'm going to substitute this because I want the input impedance as a function of who? Of the characteristic impedance of the transmission line with the, and what? And the load impedance. Did you get this or not? So in place of this gamma, do you see this gamma? Here. In place of this gamma, I'm going to substitute what? This guy. Where is it? This guy. Did you get this or not? Oh, so this is what I get. Z naught times what? ZL plus J Z naught tangent beta L divided by what? Z naught plus J ZL tangent beta L. Clear? Now you might say, where in the world did the tangent come from? Don't make me work hard, please. This is just simple equation. Okay, here. Instead of this e to the minus j, you are going to write it as a what? Cosine minus what? J sine. Yes? And you do some manipulation, you end up with what? Sine divided by cosine, which is the tangent. Clear? Okay. I want you now to see this equation. This equation, on this equation. Now, for matched load, what does it mean when I say matched load? Matched to who? Matched to who? To the transmission line, which means what? ZL equal to what? Z naught. Yes? What is this? 1, which means what is the input impedance? This is the input impedance. It's same thing as what? As Z0. Did you get this or not? Cannot hear you. Cannot hear you. Okay. Another way, by the way, if the question tells you that the transmission line is of infinite length. Of course, we don't have a transmission line of what? Infinite length. Did you get my point or not? But if you do have a transmission line of infinite length, or the question give you that, you model it as a what? As an input impedance. In other words, the input impedance to that infinite length transmission line will be the same as what? The characteristic impedance of the line. Did you get this or not? Did you get this or not? In other words, if I have like this, and we will discuss this next time, I'm running a little bit short. I have a transmission line here, followed by another transmission line. Why did I put this dot, dot, dot? What does it mean? Infinite length. The impedance looking at here is what? Z naught. Of this line. Of this line. In other words, if this is Z01, Z02, this will be what? Z02. Did you get my point or not? Yes or no? Okay, but we'll talk about that next time. Let's not worry about it right now. Now, I want you to see that. If the length is lambda 2, lambda over 2, which means what? A wavelength of what? Half wavelength. What is going to happen? The beta, I'll show you that shortly, is what? 2 pi over lambda. Yes? The length is lambda over what? 2. So what do you get? You get tangent of what? Pi. But tangent of pi equal to what? 0. So what do I have? This is non-existent. This is non-existent. Z naught. Z naught cancels and I end up with what? 0. Did you get this or not? So if you do have a transmission line with a length of half wavelength, it means as if it is what? As if it is not there. You can what? You can remove it. Do you follow me or not? And you put the load directly to the line. To the source. Clear? No response. Okay. I want you to see this. If the length is a quarter wavelength, a quarter wavelength, then what will this one be? This will be infinity. Yes? Because it's tangent what? Pi over 2. If this is infinity, it means this one and this one are negligible as far as infinity is concerned. Which means I can cancel the J with the J. This one is what? What do I end up with? I end up with Z naught equal to what? ZL, Zn, the whole thing what? Square root. Did you understand where this came from? Where? Tell me, where did it come from? This is negligible. This cancels. Yes or no? So the ZL comes in here, the tangent beta L cancels. ZL comes in here, I end up with what? Z naught equal to what? ZL times what? Zn. Clear? No response. Clear? Oh, now, let's see if you can help me here, and then we'll continue next time. ZL equal to what? 0. Because ZL equal to what? 0. What do I have? I have Zn equal to what? J Z naught tangent BL. Did you get where this came from? From this equation. If you plug in ZL equal to 0, this one is gone, this one is gone, Z naught with the Z naught gone. So what do I get? J Z naught tangent beta L. Yes? Inductive or capacitive? Or does it depend? It depends on the value of L. So if you look at the diagram, very quickly, I will show you. Okay.
Oh, I'm just, my head's up, it's about 4.
If the beta L is between, if the lambda is between if the length is between 0 and a quarter of a wavelength, it is behaving as a what? Inductor. Yes or no? If it is between pi over 4 to pi over 2, it is behaving as a what? Capacitive. Did you get my point or not? Yes or no? Which means what? It means that you could choose the value of inductor if you don't have it by using the length of a transmission line, a proper length of the transmission line, and you what? Short circuit it. Yes or no? Okay. Or if you open circuit, which means what? ZL equal to what? Infinity. What is the equation here become? If ZL equal to infinity, this is negligible. This is negligible. ZL cancel with each other. So what do you get? Minus J Z naught cotangent beta L. Did you answer where this came from? Here. Z naught minus J Z naught cotangent beta L. And here is the other way around. In other words, if the length is between 0 and what? Pi over 4, it is behaving as what? Capacitive. If it is pi over 4 to pi over 2, it is behaving as a what? Inductive. Did you get my point or not? Okay. Did I run out of time?
Yeah, unfortunately.
Not get any response. Let's continue.
No,
Did
yeah.
you say yes?
Yeah, we did. It's about like 4:52-ish.
What did you say? Oh, 2 minutes passed? Okay. We'll continue this next time. Clear? No response. Clear? Okay.
And this concludes EE 544 on Thursday, February 27, 2014.